alive to date, still takes care of his wife. And David is also working with me in recreating a prototype which should be finished at the end of December. And the same prototype as the last one that you saw that left. What I did is I said, well, okay, it's a wonderful story. It's got a lot of guts and things like that, but is there anything in the world right now that's correlating to the information that he brought us, which was absolutely non-technological, but it sure was talking about magnets and magnetic fields. So I started to research. This man is called Wilbur Smith. Wilbur Smith is a very, very prominent Canadian engineer. He also helped design the FM radio station that we have today. He was hired by the government, the Ministry of Transportation, to do all of that work, and received an award shortly before he died. And so Wilbert was interested also in unusual form of energy. Well, not just Wilbert was interested in an unusual form of energy, the Department of Transportation was interested in that, and the US government was interested in that as well, and working in correlation with the Canadian government. So Mr. Smith started to look around and find out whether or not he could find sources of information that could tell if there's any type of unusual source of propulsion, because also he was interested by flying objects. So after doing some research, subventioned by the Canadian government, he found that there was a possibility, and information was given to him, of unusual coils arrangement that would create electrogravitational energy. Energy that seems to be appearing from nowhere or disappearing to nowhere. So we'll move on to the coil configuration. This is called a Hooper coil, Hooper-Smith coil. Wilbur Smith came up with the coil, and Hooper was the one that experimented on it. What this coil is really, what it is, a tube of about 1 inch in diameter, and I'm going to try not to get it too technical, so you don't have to get scared. This is a tube of carton board, 1 inch in diameter, and what you have around it is a double wire wounded in one direction, you can see at 45 degrees, wounded in one direction, and then wrapped back into the other direction. Well, what you can do is you can actually have two sets of cables, one here that starts and wraps this way, and one there that starts and wraps on the top. Can you see the configuration here? That's very important. Vector angles, magnetic field opposing each other at different angles. This is done electromagnetically. David was doing it with magnets. And we're not trying to reach, we're trying to explain why he came up with that technology. Now we'll move on to the next slide. This slide here is showing the actual wires themselves. You can see the wire goes down from the bottom there, up, returns, and comes back. So every time you energize this wire, your B field, your magnetic field, is canceled. Also, you do the same thing with this one here, and you wind it around that coil the same way you saw it, and by applying electricity to this coil in frequencies, you would cancel out, at vector angle, the magnetic field. Let's move on to the next slide. This is the configuration that you can connect the wires in. You can connect them in parallel, in series, you can connect them so that they all oppose, or you can do whatever you want to. But a factor that's very important here, none of these coils can be put together so that the one coil powers up the second coil. Because the magnetic field in the first coil is actually getting rid of the magnetic field, the second coil can't pick up anything. So therefore, you can't have coupling. You can't couple these coils together. Another factor that was very interesting about these coils is that Mr. Smith applied frequency to them, and he would apply a lot of power to these coils, and somehow the coil wouldn't heat up, and somehow the electromagnetic field wouldn't go anywhere. There wouldn't be any electromagnetic field. So why did they give him the information? Well, he found that using some of these coils, it would get very, very unusual effects. First of all, the energy not going anywhere somehow, not heating up after putting the energy into the coil. And his last question was, well, where does the energy go? Some people then carried on to research on that. So we'll move on to the next slide. This is a drawing made by a man called Tom Bearden. Mr. Bearden is a rocket scientist. He works for the US and is still working today. And he's one of the men that has advanced some of the most possible and most plausible technology, I mean not technology but theories, as far as what happens when the magnets are opposing each other, when the fields are opposing each other. Mr. Bidden says that if you take a medium, and a medium can be a magnet, a crystal, anything that's nonlinear. Nonlinear means that something that's made out of different little objects, means like it may be a magnet's made out of powder, for example. Let's imagine that now this is a magnet. Magnet would be, let's say, 2-inch long, half an inch high by about an inch wide. What you do to this magnet, you call it stressing. We call it stressing. This magnet would be barium ferrite. What barium ferrite is the magnets we find in our little remote control cars. They're very, very cheap magnets we find on speakers. Those are the type of magnets we're talking about. This piece of magnet here would then be stressed with pulses of electromagnetic field. As the magnet is stressed, somehow the inside of the magnet starts resonating at the nuclei level. What then you do is you apply a very, very, very tiny amount of magnetic field into that magnet. And what you get on the same spot where you apply it is a huge amount of power, a huge amount of reflective wave. The reflective wave is not magnetic. It's electromagnetic. That means it doesn't show up as a magnetic wave because the magnet would be oscillating and would produce radio waves that you wouldn't believe because the power here is about 1.5 million times the amount that you put in. So you cancel all the radios and all the things around it. No, it shows up as an electrogravitational field. Like it behaves a little bit like static electricity, but it's not. We're still trying to explain what it is, but we sure can tell what it did. We'll move on to the next slide. Now, remember when I said about Mr. Wilbert Smith and Hooper? Hooper is the man that demonstrated that if you cancel out the magnetic fields, and I shouldn't use canceling here, I should use opposing magnetic fields, in the same manner as you saw in the coil there that I previously talked about, he found that by opposing all these magnetic fields, somehow he would get electricity at a distance. Now, electricity popping from nowhere. What he did is he took a can of metal, and it wraps in wires back and forth like you saw, so that when you apply the electricity to it, all the magnetic field is opposing, therefore no Gauss, no magnet field around the can there. And the can's made out of metal, so it's shielded, like we shield the Faraday cage, for example. On the outside, he puts a piece of paper that just wraps around it, and then he puts another round rim of metal around that, so now we have like some type of a little capacitor. Theory and the science field says that if it's all shielded electromagnetically and magnetically, you shouldn't have anything on the outside. What they did, he went even further. They shielded everything on top of that, and every time they would apply current into that coil, electricity would show up right on the outside between the plates of the capacitor. Well, it didn't make sense because there wasn't supposed to be electricity there. But proportionally to the amount of current applied to the coil inside, the electricity would start to build up around the capacitor and go down as you lower the current. Now, this discovery is absolutely incredible. Repeatable on the bench. It's very simple, yet nobody's bothered to do it. Nobody's bothered to reach beyond that. I'm trying to understand, why do we have electricity popping out there for no reason outside of the actual field? So let's move on to the next slide. This is what's inside that, we'll move on. Okay, well, that's good enough, Dwight. This is what's inside that can there. Can you see there you have the insulator right there, and then you have another can basically open at both ends, wrapped around it, so insulated electrically from this. And inside you have your wire going up and down, and these are your two wires resulting from this running up and down, and that's the current applied to it. And then you have your isolator, and what you do is you read the electricity between this connector here and that connector there, and then proportionally to the amount of current you put in, and this is all sealed, of course, you can see it just for the sake of seeing what's inside. This is all sealed, and electricity starts to show up as the more current you put in. And this is not a AC field, but excuse me, a DC field, which is even more unusual. Let's move on to the next slide. This is a very, very interesting machine. This was made by the Swiss people. It's a religious community, and they have scientists in that community, and they have come up with a machine that's very interesting. What this machine does, and it fools a lot of people, is that what you have at the back there is the Wimshurst principle. Two discs, counterclockwise, rotating, like you can see at my table there, is the same thing. And what it does, it produces an electrostatic field that produces an arc, with an arc gap produces a spark of electricity. Now, of static field. Now what happens is that as this field gets charged up, inside these very cans, what you have in there is donut magnets that have been stressed and prepared so that when you wind a coil around it, you can activate the coil with a small electric pulse. Well, they were really clever because it fools a lot of people. An electric pulse is very nice from this type of static machine. You can also determine how much static pulse you want to have for the frequency and also how fast your disc can go. You can keep that all stable. They were clever because they thought, well, how can we make 60 cycle? Well, why don't we take a Wimshurst machine, change the arc gap, we're going to have 60 spark per second. What they do is they take the spark and inside they spark the coil that's wrapped, the electromagnetic coil that's wrapped around the magnets. What that does, it zaps the coils, and then after that what happens is that the magnet receives this information and somehow resonates and sends out this unusual pulse. Now this machine here takes about 500 milliwatts input, and it puts about 3,000 watts of output. There's no input connected to it. It continuously puts it out, and right now the people from Switzerland are actually using these machines to power up their community. Let's move on to the next slide. We'll pause on this one. This is a small first model they made. You can see the cans again, the same thing. All the energy comes from there. This one is very small, it's about 6 inches square, and it produces 500 watts of electricity continuously. Let's move on to the next slide. We'll pause here. This was, I wanted to take that clip to show you exactly what the electricity looked like from that big machine that you saw there. So remember, this machine produces about 3,000 watts of electricity, continuously output, no input, and the way the discs are regulated is by taking a little bit of that electricity, power up a little motor, and if it's regulated, the motor will spin always at the same speed, therefore have a regular rotation, and therefore have a regular output. So here they demonstrated a light bulb lit by this type of electricity. Let's move on. Now look here at the electricity jumping. Okay, we'll pause here. By the way, when you short out the wires on this machine, the machine doesn't stop turning or it doesn't slow down. It has nothing to do with actual force. It has to do with nuclei, the nuclei that forms these molecules that forms these magnets. That's where the energy is actually being transferred to. So it's not like you put so much electricity, you get so much out, or you put so much force, you get so much out. The force is already in there. The energy is already in the magnet. It's born that way. So that's what we're using for the transfer of energy. Now, another machine, a man named John Searle from England. John was a very, very clever engineer. He said, well, you've noticed that some of the design of the motors that he built for big companies, some of them would have less EMF than other motors. That means that would require less to run than other motors. He found that pretty fascinating, so he started to experiment on that. And then what he did is he built this machine like this, which is about 15 feet in diameter. And then inside, he would build these slug magnets, which basically looks like this, and would be, of course, shorter and a bit bigger, but it's round like this. And the magnetic field would actually swirl around it. So he'd take the magnet itself and then magnetize it with the coil going around in a swirl motion. So you would have a south pole going to a north pole, rotating around the magnet. What he did is he then take these slugs and put them inside rotating rings. So the slugs actually rotate upon themselves. He would rotate the rings inside, so some slugs would rotate in one direction, some slugs would rotate in the other direction, but the slugs inside between the two rings here would see themselves rotating side by side, and some of their field would cancel. Let's look at a cut view of that machine.